He will not force.
Hello and welcome to the 2014 Simonyi Lecture. Many thanks again to the Playhouse for hosting us and to the Amalur Foundation who make the finances of this possible. My name is Marcus de Sotoy and I'm the Professor for the Public Understanding of Science here in Oxford. And as the Professor for the Public Understanding of Science, people tend to think that I know everything about science and can tell you about it. But I find I don't, and I was asked to take part in an energy debate at the Hay Festival a couple of years ago, and I needed something to help me to mock up on what is quite a complex debate. And somebody recommended this wonderful book called Sustainable Energy Without the Hot Air by tonight's speaker, and I fell in love with it immediately because the opening part is called Numbers, Not Adjectives. So a book for me as a mathematician. But certainly this helped me very much to negotiate my way through what is a very complex issue. So I thought, what a great person to come and bring to Oxford to help us all to understand climate change and sustainable energy. So I'd like you to give a big Oxford welcome to David MacKay, who's going to be talking on why climate change action is difficult and how we can make a difference. David is Regius Professor at the Department of Engineering in Cambridge, and more interestingly, he was also former Chief Scientific Advisor to the Department of Energy and Climate Change. So, David, thank you very much.
Thank you very much. Thank you. Thank you all for coming. I'm a physicist and an engineer, and most physicists and engineers love back-of-envelope calculations. And I'd like to start my talk but just by showing you as a little pre-talk a back-of-envelope calculation to illustrate the sort of thing I like to do. I was having a conversation with some bods from Shell, and we were discussing transport policies and the idea that Europe has of switching us over to biofuels. And one of us said, if we grew the biofuels for the cars on the verge of the road, how wide would the verge need to be? So this is a lovely example of a back-of-envelope calculation, just to get a sense of scale of what we're imagining we might do. So you make up some numbers and you work out an answer. So let's make up numbers. So we said, let's have the cars go at 60 miles per hour. Let's assume they do 30 miles per gallon, which is the average of new European cars today. Let's look up on the internet what the productivity of European biofuel plantations is. It's 1,200 litres of biofuel per hectare per year. And finally, we need a spacing between the cars, and then we've got all the numbers we need to get an answer. You don't need to specify how long the road is, because the longer the road is, the more cars there are, and the longer the biofuel plantation is. All right, so what do? Well, you take the first number, and you divide by the other 4, and take care with units, and you'll get an answer, which is a length, and it's 8 kilometers. So given these assumptions, that's how wide the verge needs to be. And I love this sort of back-of-envelope calculation, because even though the numbers are made up, it's enough to make you say, maybe it's not as easy as just saying, oh yes, we'll get ourselves off oil by switching to biofuels. Maybe we need to think about some other options, or maybe we need to really hammer on some of these numbers and say, well, yes, we can switch to biofuels, but they better be next generation biofuels, which have to be so much better per unit area. And we need to think carefully whether we could do that, or can we make the vehicles far more energy efficient? Maybe transform our assumptions about people going around in cars all the time. Okay, so, and for those of you who want to go away with a homework problem, I don't know if you still like homework, you could ask yourself another question. What if you switched to electric cars? Then how many windmills would you need every, what would the spacing between the windmills be? How many windmills per mile would your road need? So that's a homework problem. And I wrote a book full of back-of-envelope calculations to try and help people understand in a very clear, transparent, straightforward way how to compare energy options with each other. Energy options on the supply side for getting off fossil fuels, and demand side. What does your lifestyle require, and where do you want that energy to come from? All in exactly the same units. So I wrote this book. It's free online, and you can buy it from my publisher in the foyer. If you want to make him happy, please do. And because I gave it away free online, it's generated a lot of goodwill, and volunteers have translated it into lots of other languages. So if you speak Chinese or Japanese or Slovak or French or Hungarian, there's also translations available in those languages. And I wrote this book because everyone was getting emotional about energy options, and I was a bit distressed by the things I heard on the radio. People were saying things that didn't add up. I don't have anything against emotions. Emotions are really important. They drive things along, but we need facts as well. So I wrote this book and ended up becoming a senior civil servant, which wasn't the original plan, but it was a lot of fun, and I could tell you more about that. So tonight's talk is going to have 3 bits. I'm going to talk about climate science, I'm going to talk about energy arithmetic, and then I'll talk about innovation. And by the end, I will have told you about 6 or 8 reasons why things are difficult, but I hope I won't depress you too much. I hope I'll also keep some upbeat messages in there about we can do it. So first, some bad news. Let me tell you a little bit of climate science, which you may not have heard. This, I think, is one of the most important figures from the IPCC's 5th assessment report, which came out over the last 12 months. It's a figure which shows how big climate change is going to be, summarized by one number, which is the global average surface temperature increase. Of course, that's not the only thing that climate change is about, but it's a useful summary variable. So this is how big is climate change up here. We've actually lost a little bit of text off the left-hand side. If the technicians could possibly do tweaky and get us an extra 10 pixels, then that would be nice, because it says temperature anomaly relative to 1861 on the left-hand side. Okay. And it shows how big climate change is as a function of not the emissions rate, but as a function of cumulative emissions, so the total amount of carbon that humanity has emitted since the Industrial Revolution. The top little left graph is what people often show. It's the emissions rate, which has been going up and up and up, black line, and then in the future could carry on up, red line, worse than business as usual, or it could sort of stay constant-ish, yellow line, or blue line, it could come down, or dark blue line, it could really come down. So there's lots of possible futures, and humanity has a choice what we do with ourselves. So for those 4 possible futures, what's going to happen? How big is climate change? Well, the unfortunate answer is that it's proportional to cumulative emissions. That's what all these lines show. And what that means is if you want to halt climate change in terms of global average temperature rise not going up anymore, then you've got to limit cumulative emissions, and that means the emissions rate has to drop to 0. All right? And that's disappointing because I think a lot of people imagine that climate change action means reducing emissions. 20% reduction by 2020, 80% by 2050, or maybe 50% for some countries. So reduced by 50%. And it would be lovely if that worked, but it doesn't, according to these climate models that this is all based on. If you reduce your emissions by 50%, which is the light blue line, then your cumulative emissions are still going to go up and up and up. You will have slowed the rate of climate change, but climate will still be changing under the light blue scenario. The only way to get emissions to stop is to do something like the dark blue line, where emissions actually reach 0 or even go negative. Okay, so that's science fact number 1. It's based on the literature. It's your own local Miles Allen and co-authors who did some of this work. This is a picture from Miles Allen's original Nature paper showing the massive uncertainty. I forgot to talk to you about the pink sausage. So this big pink sausage here, it shows the uncertainty about what this overall climate sensitivity is. So climate science is uncertain. We don't know what the slope of this line is. It's somewhere in the pink sausage, and that's shown visually in this Miles Allen paper. If you change from one climate model to another climate model, you get a different sensitivity, but they all have a straight line. So they're all telling you that if you want to cap climate change, you do need your emissions rate to drop to 0. Okay, so that's sort of bad news. And here's what it could look like, summarized by the IPCC in the summary synthesis report that came out a couple of weeks ago. So you've got your emissions rates, and that can lead to, if you follow the worse than business as usual red line, then we're up to possibly a warming of something like 4.5 degrees by the end of the century. Or if you take the radical climate change action, which ain't easy, the dark blue line, then you could stabilize things at who knows what, but something about 2 degrees-ish. So, some people say 2 degrees, that doesn't sound too bad, and it's important to try and get an understanding of the impacts of 2 degrees. And one way of visualizing what a 2-degree global average temperature rise means, obviously the difference between day and night on a typical day in England is far more than 2 degrees, but actually this 2 degrees is a much more important 2 degrees. Here's a graph of what the global average temperature has been doing for the last 20,000 years, and you can see 20,000 years ago it was about 3 degrees colder globally. And what did that planet look like? Well, it was quite a different planet. For example, the sea level of the whole world was 100 meters lower than it is today. Why? Well, because the Northern Europe and North America had 2 miles of ice sitting on top of it. So that was the last ice age. So a temperature change of 3.5 degrees or so is the difference between an ice age and today. And if you say, oh yeah, let's have another 2 degrees warming, who cares? Then you're taking yourself off. Or if you say 3.5 or 4.5, I don't care, then you're actually saying, I'm happy to visit a planet that's as different in the other direction from today as the ice age is. That's a photograph of the Earth 20,000 years ago on the right there. Let me visualize it another way for you. Does anyone remember the summer of 2003 in Europe? Were you here in Europe in 2003, and do you remember it? So climate change isn't going to be uniform over the globe. The projections are extremely uncertain for any one country, but the global pattern is that the poles will warm, the North Pole will warm far more than the rest of the globe, and the land will warm more than the oceans. And so we could ask the question, what's this going to imply for Northern Europe? In 2003, we had a heat wave, and a load of people died, and there were droughts and so forth. So it may have been a memorable experience for you 11 years ago. And you could ask the question, under these climate models, if we believe the climate models are right, then what sort of frequency will this sort of event have in the future? This was the hottest summer in Northern Europe ever recorded. So it was at least 1 in a 100-year type of event, a very rare event under the old climate. So under the red trajectory for global emissions and the dark blue trajectory, what's the difference between the future frequency of summers like 2003? Well, here are some graphs coming out of the Hadley Center's model of what summer temperatures might do in lots of simulations of the planet, focusing attention on Northern Europe. So here's the area on the map. And this is under the dark blue trajectory. Temperatures are forecast to carry on increasing. I'll just pop the mouse on 2003 for you there, and then I'll slide it across so you can see where that sits in 2050, which is in the lifetime of many of us here in this room. In 2050, this model is predicting that even on the dark blue trajectory, half of all summers will be significantly hotter than the hottest summer ever in Northern Europe. So maybe that makes you sit up a little bit and have a bit of a feel for what that world in 2050 might be like, let alone 2100, let alone under the red scenario, where if we do the above business as usual red emissions trajectory globally, then look where the mouse is. 99% of all summers are going to be hotter than the record-breaking hottest summer ever by 2050. And by 2100, all summers will be substantially hotter than that level. So that's what 4.5 degrees looks like for Europe, according to this climate model. And we don't yet know the climate sensitivity. We don't know if this model's right, but it may be. So that's climate science. And so to summarize what I've told you so far, why is climate change action difficult? We're not just talking about emissions being reduced a little bit, 5%, 10%, have a little trading scheme and sort it out. No, not a 10% reduction. 0 is where we're going. We need a 100% reduction in emissions to have actually solved the climate change problem. Moreover, if you take the central point, the central slope within that sausage, then you've only got 1 trillion tons of carbon to go, and we've already emitted about 500 billion tons, thanks to land use change and fossil fuels and cement. And so half the budget's gone for the so-called 2-degree outcome, which a lot of attention has focused on. So keeping temperatures below 2 degrees. Roughly half the budget is gone, so there's actually not very long. You need to do a sudden handbrake turn between emissions steadily rising and getting them to come down again, if you're interested in having a decent chance of achieving the 2-degree objective, but I put a little asterisk on there, batteries not included, some conditions apply. We don't know the climate sensitivity. So whenever anyone says, oh, we're on track for 2 degrees, bear in mind, we don't know the climate sensitivity. So even if someone told you a budget and said this is the 2-degree budget, the one thing you can be sure of is that budget won't get the global warming to be 2 degrees. It'll either be bigger or smaller, and we don't actually know yet which. Okay, so we get emotional, and we need some numbers too. I'm emotional about climate change, but I'm here to try and help with the numbers. So let's talk about energy arithmetic. And I'd like to give you a rough guide to sustainable energy, where I'll start off by doing everything per person. So to avoid answers involving millions, billions, and trillions, which I think most people don't have a feel for at all. They all sound about the same, don't they? They're just big. They are actually different, but people don't understand that. So let's not use those numbers. Let's do everything per person, and let's choose units so we don't ever get things coming out in millions or billions or trillions. And let's do deliberately inaccurate calculations, do everything to one significant figure, because then it's easier to remember things and compare them. You don't want too many numbers having to be memorized. I'll measure energy in kilowatt hours. That's what your electricity meter reads energy in. And if you have a gas bill and actually look at it, it probably converts your gas usage from cubic feet into kilowatt hours as well. So it's a standard unit that households can actually find out if they look at their bills and their meter readings. And I'll measure power, which is how fast we use energy in kilowatt hours per day. The physicists and engineers in the audience may now spit because they would say, oh, why don't you just use an SI unit like the watt or the kilowatt? And there's 2 reasons for this. First, if I tell a typical person, look, the average British person has a power consumption of 5,000 watts, they'll probably say, is that watts per month or is it watts per year? Because they don't know what a watt is. They don't know that the watt has got the per unit time already built into it. So people don't know what a watt is. But if you say kilowatt hours per day, it's very clearly a rate of using something, so people understand it better. That's the first reason. And the second reason is the numbers come out in 1s and 2s and 10s if you use kilowatt hours per day. So that's another reason I like watts. Kilowatt hours per day. Watts are too small, kilowatts are too big. So here's some everyday things that people do that come in small numbers of kilowatt hours. If you take a standard 40-watt light bulb and use it for 24 hours, you have used 1 kilowatt hour of electricity. If you eat food, the chemical energy in the food you eat amounts to about 3 kilowatt hours per day. If you take 1 hot bath, that's 5 kilowatt hours of heat energy. If you take a litre of petrol and set fire to it, you dissipate 10 kilowatt hours. And if you have a Coke habit and you drink Coke and you chuck the cans away, the embodied energy, the energy required to make the aluminium cans that delivered the Coke to you, is about 2/3 of a kilowatt hour per can. So that's some everyday choices. Here's a few more. If you've got a car and if you drive at 100 kilometers a day, I'm not saying everyone does this, but if you do that, then if it's an average European car, you're using 80 kilowatt hours per day. If you have a house, British or North American are about the same, you might be using about 80 kilowatt hours per day to run everything in the house. And maybe an extra 3 kilowatt hours of energy is required to operate the cat in the front garden there. If you fly, you use a hell of a lot of energy on the day when you fly, which is incomprehensibly large. But to make it comparable, we can say, well, how often do you fly per year? Let's, for example, say you do London, Los Angeles, and back once a year. Then take that huge amount of energy, spread it over the year, and you find it's 26 kilowatt hours per day for one person. And fourthly, here is something black, which gets quite a lot of attention, and this is one of the things that drove me to write a book. For example, the Mayor of London said, if all Londoners unplug their mobile phone chargers when they're not in use, we could save 31,000 tons of CO2 and £7 million per year. Clearly, thousands, millions, it's enormous, it's very important. It's on the list of 7 things you can do for DIY planet repairs. Okay, does this belong in the top 7 things we encourage Londoners to do? Well, if you're willing to do arithmetic, you could say, what's the population of London? 7 million. So 7 million per year divided by 7 million people is £1 a year saving. Okay, that's not 0, but it's maybe not. Does it get into the top 7? Let's think of it another way. Is the phone charger a planet-destroying thing as evil as Darth Vader? Let's check. Let's compare it with a car. And if you work out the energy saved by the feat of energy conservation of actually unplugging the mobile phone charger for a whole day instead of leaving it plugged in without a phone attached to it, the energy you have saved is exactly equal to the energy used by driving an average car for 1 second. Both of those are equal to 0.01 kilowatt hours. Okay? I'm not saying don't switch it off. Switching off vampires at home does help, but be aware how small it is compared with other things that might also be in your lifestyle. So just to visualize it, here in red blobs are how big those last 4 things are. Car, house, flying, phone charger. So probably the phone charger doesn't deserve to be on that top 7 list of things you can do to do your bit. The total footprint of the average UK person, if you just average over everyone, all forms of energy consumption, comes to about 125 kilowatt hours per day per person, which you can visualize as 125 light bulbs worth of energy consumption. And you can split that if you want a quick cartoon, if you want to have a quick conversation about what are we going to do, well, it's transport, heating, electricity, roughly a third each. And that's how much energy is going into making electricity. The actual efficiency of the electricity making is about 40% or so, so the actual amount of electricity we use is about 17 kilowatt hours per day per person. Electricity gets a lot of attention, but actually it's only about 1/3 or 1/5 of the problem, and the other 2/3 definitely needs attention too. And today, we get 90% of this energy still from fossil fuels. And if we're interested in climate change action, and if we're interested in security of supply, then we need to be getting off that 90% fossil fuel dependence. Okay. And there's one more thing we need to include in our rough guide. We need to think about land areas, because as my opening example with the verge, with the biofuels growing on it, illustrated, some renewables have land area implications. So we need to talk about population densities, and those vary. The UK's is 250 people per square kilometre, or if you want to say per person what area we've got, it's 4,000 square metres per person, which is half of a Premiership football field per person. And I'm going to talk about power per unit area, how much we consume per area and how much we can generate per area, and that I will measure in watts per square metre. So now we're ready to continue with our rough guide. I'm going to show you a map of the world now. In this map of the world, the vertical axis is the energy consumption per person of a region. The horizontal axis is the population density of the region. And the size of each blob is the land area of the country that I'm showing. And the axes are both logarithmic. So as you go from gray line to gray line to gray line, you're going up by a factor of 10 in population density. So there's a huge diversity of population densities of countries around the world. And vertically, again, this gray line to that gray line is another factor of 10. So what you can see is there are some countries with very low population densities and huge per capita consumptions, like Iceland, Canada, Australia, consuming 200 or 300 light bulbs per person. Bahrain, top right, has a population density that's 300 times bigger and consumes about the same per person. Bottom right, Bangladesh has the same astonishing population density as Bahrain, 1,000 people per square kilometre, but it's consuming 100 times less energy per person. Bottom left, there's no one. But there used to be countries down there, I'm sure, because another message of this diagram is progress. I'm going to add some little lines here, these little blue lines behind Sudan, Brazil, Algeria, China, India, Bangladesh, Portugal, Libya, Australia. They're showing 15 years of progress from 1990 to 2005. What happened to population density? What happened to per capita energy consumption? And you can see lots of countries are going up and to the right. Off to join, perhaps, us and Germany and Japan, who are 3 fairly atypical countries with slightly above average population densities and slightly above average per capita consumptions, though not as high as that of the United States and Australia. So maybe the UK is quite an interesting case study because it's staying fairly steady in a location on this diagram that other countries might be coming to. And anyway, we've got to sort ourselves out. We need to have a plan for the UK, and Germany, I hope, could have a plan, and Japan needs one too. So I'm going to now focus in on these countries, and I'm going to start talking about power per area. How does this work? If you take the population density of a region, and if you multiply it by the energy consumption per person of that region, the product of those two numbers is the power consumption per unit area of the country that you're talking about. And because I've got logarithmic scales here, it turns out that lines of equal power consumption per unit area are these pink lines with slope -1, So, for example, the power consumption of Saudi Arabia is about 0.1 watts per square meter, and so is Mexico's, and in 1990 so was China's, and in 1990 so was India's, and in 1990 so was Bangladesh's. They all were consuming 0.1 watts per square meter. So that's an interesting figure, sort of baseline, and actually 80% of the world's population lives in countries that are above that level. So 0.1 watts per square meter. Most countries are using more power than that. And we are up at 1.25 watts per square meter of power consumption. Why do I bang on about power consumption per unit area? Well, because renewables, many of them, require some land area, and it's interesting to compare numbers like 0.1 and 1.25 watts per square meter with the power generation that you can get from renewables. So let's now shrink this diagram a little bit and then add some green lines to show what renewables can do for you. So energy crops. There's lots of energy crops, and it depends if you fertilize them, and it depends how much water you've got, and so forth. And if you do genetic engineering and crop modification and so forth, maybe this can be improved. But as a very rough figure, half a watt per square meter is what you get from energy crops. All right? And if you're good at arithmetic, you'll know that that's smaller than 1.25 watts per square meter. So what's this saying? If you wanted literally to power the whole UK on energy crops alone at today's level of energy consumption, you need 2.5 UKs to grow the energy crops on, and then you could power the UK. All right? Next, wind, 2.5 watts per square meter. And I don't want to lose time, but I do have plenty of data backing up that number. So it's 2.5 watts per square meter. What does that mean? Well, that's twice as big as 1.25 watts per square meter. So if you literally wanted to get absolutely all of today's energy consumption from wind alone on average, then you need wind farms with half the area of the UK. All right. Sunshine. The raw power of sunshine is way up here. It's 1,000 watts per square meter if you are at the equator at midday. So people often emphasize that and say how enormous the sun is and how you only need so many minutes of sunshine to do something or other. And it sounds very impressive. But let's be careful with a little bit of reality that you can't. We're not all at the equator, and it's not midday all of the time, and we need to include the efficiency with which sunshine can be turned into useful forms. So, coming back down here, the raw sunshine at the equator is about 250 watts per square meter, 4 times smaller because it's midday about a quarter of the time. In the UK, we're not at the equator, we're further north, and it's cloudy. The average power of sunshine in the UK, day and night, year-round, is 110 watts per square meter. So that's what we start with, and now you include a realistic efficiency of how much of that power per unit land area you can actually get out, taking into account the efficiency of the solar panel or whatever it is, and also how close together you can put your solar panels, which determines the sort of filling factor of your landscape. So if you go and use your roof, you will get about 20 watts per square meter. So this is real data from a roof in Cambridge. This is 20 watts per square meter of roof area. Grand. And when you, one thing to bear in mind, which I'll come back to later on, is that the average output isn't the same as the actual output. It varies a lot throughout the year. You get about 9 times as much in the summer as you do in the winter. So that's important to bear in mind if you are trying to make a plan that will add up every day of the year. Anyway, 20 watts per square meter. Now, if you want to adopt the traditional Bavarian farming method, you'll also leap off the roof onto the countryside and cover the countryside with solar panels. This is Bavaria. And this Bavaria solar park, according to its press release, delivers about 5 watts per square meter of land area. That's less than 20 watts per square meter because there are gaps between the panels to let the maintenance people get in and to make sure that the panels don't shade each other. They want to tip them up to point nicely at the midday sun, and they don't want them shading each other because that would be a waste of money. Here's another solar park in Vermont for which real data is available free on the internet. Lovely company. And so you can work out the power per area of this extremely modern solar park with panels that actually track the sun. And the answer is 3.8 watts per square meter. That's in Vermont. And here's lots of data for lots more solar farms. And the rough summary is for solar panels in cloudy countries like the UK and Germany, shown in magenta and Cambridge blue bottom left, you get about 5 watts per square meter of land area from your solar parks. there's a Japanese park or two in red, which are giving about 10 watts per square meter. And in sunny countries, this axis is here is how sunny the location is. You go to Italy and Spain and then America in puky yellow, and you're up at 10 watts per square meter for quite a lot of these farms. So 10 watts per square meter for sunny countries, 5 watts per square meter for dark countries. The very best you can do is these little pluses, which are roof-mounted systems, which, as I said before, can deliver 20 watts per square meter. That's one in Hawaii, which is wonderful. Okay. So what does that mean? Going back to this diagram, you get 5 watts per square meter from solar parks. So if you wanted to match today's total primary energy consumption with the output of solar parks, you need a quarter of the land area of the UK if you want those to be solar parks in the UK. And bear in mind that fluctuations issue I mentioned. And some people say, oh, he must be wrong, he must be anti-renewables. I'm not anti-renewables at all. I love them. I love renewables. I also love arithmetic, and I love truth. And so I've got data to back up everything I'm saying, and I want us to have a plan that adds up. So if anyone can give me better data, just send it to me, and I'll add it to the diagrams. What else can we do? If we really love renewables, we could love them in other people's countries as well. So we could ask people in Algeria or Kazakhstan to have concentrating solar power stations, which might look like this beauty in California or Nevada. I don't know what its power per area is, because like many companies, it's secretive about its performance. But this company with lovely Stirling engines delivers 14 watts per square meter of land area with its concentrating solar power. This fantastic facility in Spain, largely paid for by Germans, I think, generates solar power at night as well as in the day by the fantastic trick of making molten salt and putting it in this huge tank during the day, and then you can carry on generating at night using the molten salt as the heat source. And it's got a power per area of 10 watts per square meter. This one in Spain delivers 5 watts per square meter of land area. And so being really charitable, I'll say 20 watts per square meter for concentrating solar power, because the literature says they could deliver that, even though none of the examples I just told you got to 20. All right? I think 10 is probably more realistic. But anyway, that's bigger than the numbers we've just been talking about. Good. But it's not that much bigger. So even if you said, yeah, let's get our power from Libya with concentrating solar power stations, you're still talking about a really substantial land area in Libya, comparable to 10% of the size of our country if you wanted to completely power the UK from Libya. So much as I love them, all renewables are diffuse. They have a small power per unit area. And here's a list of some of the powers per area I've mentioned and some more which I could hop to in the questions if you want to hear about tidal power and things like that. Okay, so if you want your plan to focus on renewables in the future, you have to be anticipating large renewable facilities. And not everyone loves large renewable facilities. And you could include other options in your portfolio. You could say, let's discuss nuclear power. And Pandora's Promise was shown earlier today here, which is a film advocating including nuclear in the mix in order to take successful climate change action. And you might be interested to know, what is the power per area of nuclear? Well, here's a simple calculation. You grab an Ordnance Survey map, you find a blue kilometer square at Sizewell, and in that there is a Sizewell B, which is a gigawatt, so it's 1,000 watts per square meter. And I can give you a more detailed calculation, including the mine and the waste store if you want. But that's a ballpark figure. You can do higher power per area than 1,000 watts per square meter with nuclear in terms of the generating sites themselves. And how does that compare with wind? Well, it's a factor of 400 bigger than the power per area of wind. So wind farms may be found intrusive by some people. Some people don't like them because of the intrusiveness. Nuclear power is 400 times less intrusive in the landscape in terms of land area occupied. But, of course, power per area is not the only metric that people care about, and nuclear has popularity problems for other reasons than its power per unit area. And we need to take into account all those views and hopefully achieve consensus as a society and make a plan that adds up. And I want to remind you that, yes, nuclear has popularity problems, but so do renewables. Here's a photograph of a consultation exercise in full swing in the little town of Pennycook, just south of Edinburgh, and you can see the children of Pennycook celebrating the burning of the effigy of the windmill, because if there's one thing the British public are good at, it's saying no. So we need a plan that adds up. All of these options are unpopular, and the way I like to think about this is in terms of levers which can give you stuff, and the more you push on a lever, the more you get. And maybe the more people are unhappy about the intrusiveness or whatever, the risk and so forth, or the cost, or whatever it is associated with that lever. So you've got all these different green levers which are sources of supply. And if someone says, no, I don't like that lever, then, well, you just need to push even harder on the other levers because it's got to add up. All right? So I'm not at all recommending a mix. I just want us to choose a mix that adds up using the basic laws of arithmetic. So I've mentioned 3 big levers here. Our renewables, wind, bioenergy. Other people's renewables, nuclear. And there's lots of other levers as well. Clean coal with carbon capture and storage, clean gas with carbon capture and storage. I could talk about that. I think it's important too. But there's other levers as well, because there's no written law that says the UK public must consume 125 kilowatt hours per day per person. Maybe we could consume less thanks to technology, or maybe we could consume less thanks to lifestyle change. And all of these options, I think, should be on the table as well. And society could agree to lifestyle change or not. And you just need to know, well, that's another lever. If you say no lifestyle change, then you have to push harder on the other levers. They're all options. So here are some red levers, which are on the red demand side. And I'm just going to rattle through an optimistic view of things you can do on the red side to sort out transport, heating, and some forms of domestic energy consumption. So first, transport, which is a third of the problem. Here's what the laws of physics say. Yes, we can reduce our energy consumption for transport. We don't have to roar around in tanks, in individual tanks. The laws of physics say if your vehicles have small frontal area, small weight per person, and if they go slowly and go steadily and convert energy efficiently between different forms, then you'll use less energy because you'll be reducing air resistance, rolling resistance, and braking losses, which is where the energy is going. Converting energy efficiently between different forms is important. Not everyone knows that the efficiency of the little power station that you're driving around in a standard car, that petrol power station, is about 25%. So turning chemical energy in the fuel into oomph at the wheels. And that's not a fantastic efficiency. So that's one thing to take advantage of. So how much improvement can we get over the tank with one person sitting in it? Here's the tank, and it uses 80 kilowatt hours per 100 person kilometers. That's a fairly standard car's energy consumption, assuming it's got one person in it, as it usually does. And some people say, oh, yes, engineers are wonderful. We can have vehicles that use 100 times less energy, no problem. And is that true? Well, let's look at some numbers. Yes, almost. 80 times less energy per 100 person kilometers is used by this bicycle with 3 people on board. It runs on biofuel, interestingly, extra Weetabix in the morning. And the person in the tank might say, no, 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 come off it, that's a lifestyle change. I don't want to operate that lifestyle change lever, even though that technology switch would reduce energy consumption. So what other options are there in the landscape of transport? Well, here's a few. You could say, oh, you want to have an individual car, do you? Well, how about you drive the eco car? Sorry, we still lost the pixels off the left. This says 1.3 kilowatt hours per 100 person kilometers. Almost as good as a bicycle. It's shorter than a traffic cone. It comfortably accommodates one teenager. And you drive it at 15 miles per hour to get that performance. And the lady in the tank over here might say, no, no, I want to go fast. So you say, all right, go fast in a train. And that's almost as good as a bicycle if it's a well-loaded train, 3 to 6 kilowatt hours per 100 person kilometers. And the person in the tank might say, no, no, I can't travel with all those horrible people. Well, can we compromise, keep the lifestyle, but somehow make things more energy efficient? Well, yes, one option is electric vehicles. Here's an electric motorbike, a car, and another car, all using significantly less energy per 100 kilometers measured at the socket. So now you're starting to worry, well, where does it come from out of that socket? If it's coming from a coal power station that's only 25% efficient, then actually we haven't really won at all if we switch to the gee-whiz. But if we have a plan to do something about the electricity system at the same time as electrifying transport, then we can make a plan that adds up and does decarbonize and does save energy as well. Okay, so that's your transport levers. There's lots of them. Heating and insulation. That's where maybe, I don't know, a quarter or so of our energy is going in the UK. Here's a crappy house in Cambridge. It's mine with the Ferrari out front. And the laws of physics apply to all buildings, and they say that the heat loss of a building is the leakiness of the building multiplied by the temperature difference between the inside and the outside. The power required to make up for that heat loss is the heat loss divided by the efficiency of your heat creation system. Standard heat creation systems in houses are called gas boilers. You put in gas and you get heat out with an efficiency of about 90% or so. And maybe they sometimes claim 95%. And that sounds great, but it's actually lousy because, and this requires understanding of physical chemistry, what you're doing is turning very high quality energy in the form of chemical energy into heat at 20 centigrade, which is what you want in your house. And that energy has much less value, and it could have been created much more efficiently. It's actually terribly efficient to do that only with an efficiency of 90%. So what can we do? We can do better than 90% heat creation in green. We can reduce the leakiness of the building, and we can reduce the temperature difference between the inside and the outside in red with an amazing technology called the thermostat. You grasp it, you rotate it to the left, and your energy consumption will go down. I've tried it. It works. Some people call it a lifestyle change. But I really urge you to try it and see what happens. You might be surprised how much you can save without actually feeling it was much of a lifestyle change. And you might get to wear cuddly sweaters as well. Right, so here's the leakiness reduction options. The first two things you could do is get the fluff men in to put fluff in the walls and extra fluff in the roof, and that might give you a 25% saving or so. Also, we've got an extra front door to reduce the heat loss out of the front of the house. So you can get 25% by these sort of changes. If you want more than 25% for a crappy British building, then you need to look at either interior or exterior wall insulation. Maybe 12 or 20 centimeters of rock wool on the outside is the sort of number you're looking at to bring the building up closer to Swedish building standards. Here's a block of flats in London getting the exterior insulation treatment. And finally, the efficiency of the heating system. I mentioned that you can do better than 95%. Here's one way to do that. It's called a heat pump. It uses a little bit of electricity to move heat from the garden into your house, a bit like a fridge moves heat from the inside of the fridge into that place where the spiders live, right behind the fridge where it's warm. Okay, so this is a back-to-front refrigerator, and it's got an efficiency of roughly 300 or 400%. So you put in 1 unit of electricity, and you end up with 3 units of heat or 4 units of heat being delivered to your house. So, and heat pumps come in lots of flavors: air source heat pumps, water source heat pumps, ground source heat pumps. So that was some heating levers, and now I want to talk about another sort of lifestyle lever, which I call read your meters. And when I was writing this book about energy, a friend asked me, how much energy do you use at home? And I was actually quite embarrassed because I was writing a book about energy and I didn't know. So that started me reading my meters. And every week I read my meters, and I started doing experiments to see what effect I could have on my energy consumption. And it blew my mind. I actually more than halved my gas consumption, as these graphs show. So in the old days, I was using 40 kilowatt hours per day as a bachelor alone at home. And then the green line, 2007, I used 13 kilowatt hours per day on average because I tinkered with the thermostat, and I was astonished. The body is not an engineering system. It doesn't have a set point. You don't need the temperature to be 19 all the time when you're at home. Actually, sometimes you might want 21, but a lot of the time you can get by on a much lower temperature, and it just depends what you've been doing, how long you've been doing it for. So now our thermostat is at a much lower temperature, like 15 or 16 or sometimes 13, and the house rule is, if anyone's cold, turn it up. And you can turn it up to whatever you want, but then it gets reset back down to 13 or 15 or 16. And that gives this huge energy saving. So I really encourage you, read your meters, do experiments. You'll be amazed how much saving you can do. And that's my number one recommendation. If you want what we can do, everyone can do this. You can read your meters and do experiments. You can do the same with your electricity. I read the meter every few hours and then did the experiment of switching off all the vampires, not just the phone charger, which is ridiculous, but also the cable modem, the computer peripherals, the DVD player that was on all the time, the stereo that was on all the time. And I found the cumulative saving from switching off all those vampires was about 45 watts, 1 kilowatt hour per day, £45 per year, which I can spend on an extra holiday in Lanzarote. So, read your meters, it's fantastic. So there's some levers, green ones, red ones, and we need to have a plan that adds up. We need to have a conversation about these levers, which of them we like. Are we happy with the lifestyle change? If no, fine, then take it off the table. You just have to push harder on the other levers. And if you don't want to switch to electric vehicles, then figure out how to make things add up, and so forth. Bear in mind the land area message that I had earlier when you're having these conversations with each other. Here's a map of the UK visualizing to scale the land area and sea area required to get 16 kilowatt hours per day per person from wind on average. Every one of these grey squares here is 100 square kilometres of wind farm in Scotland and in the sea and so forth. Nuclear power doesn't require much land area, but to get 16 kilowatt hours per day per person would be a fourfold increase in nuclear over today's levels of nuclear, or 2012 levels. The biomass to deliver 16 kilowatt hours per day per person is not just the 1 Wales worth shown in England, but another 3 Wales' worth in other countries. And solar in deserts requires a smaller area shown by these 8 hexagons over the channel somewhere, with power lines all the way across Spain and France, perhaps, in order to bring the power from the Sahara to Surrey. Each of those 16s gives you a separate contribution. If you were to do all 4 of those, for example, you'd get 64. Today's primary energy consumption is 125. So maybe you can push hard on the lifestyle levers and the demand levers to get things down, and then choose some mix of these or other technologies. And your plan that you make when you're having that conversation needs to add up, not just on average throughout the year. I was showing you year averages there. It needs to add up every second, because supply and demand must be matched somehow, or you've got to have some form of energy store to make things add up. So every month, every day, and every hour, it's all got to add up. And this is an important issue. I think I'll skip over the details of this. These are graphs showing electricity demand fluctuations, gas demand fluctuations on exactly the same scale. Much bigger fluctuations throughout the year in gas consumption than you get in electricity consumption, and that's temperature driven. The purple line there is showing temperature. So you can see swings of 60 gigawatts, if you want to put it in power stations, sort of 40 or 60 gigawatt swings in the winter in terms of our heat consumption. And meanwhile, transport demand is very steady at 100 gigawatts or 40 kilowatt hours per day per person throughout the year. So that's a steady form of demand. And then bottom left, this gray wiggly graph is visualizing what our wind output would look like if we had the same amount of wind in the UK that Germany has got. They've got 35 gigawatts. This is a graph for 33 gigawatts of wind. We've currently got about 10. So if we had 3 times as much wind, the output of that wind would be wobbling up and down on a scale similar to the current daily wobbles in electricity demand. Okay, so matching supply, second by second, hour by hour, is an issue. It's very important. People who say, oh, I just want solar power, need to think very carefully about the fluctuations in demand and supply. So I think you can see where I'm driving. Why is climate change action difficult? Points 3 and 4. Well, I feel that people are unaware of the scale of change required and the scale of stuff that needs to be built to make a plan that adds up. And that makes it harder to change climate change action because people are deluded. They've been misled by myths about things like roof-mounted mini turbines as being a significant contributor. The roof-mounted mini turbine might be enough to power your mobile phone charger, is the rough scale of it. So that makes it difficult. So we need a way of engaging people in a numerate, fact-based conversation. And when I worked at DEC, one of the things I was involved in was making and publicizing the 2050 calculator, which I would love to engage you with, but we don't have many minutes left. So I'll just show you. Here is the web front end. It's a tool with demand-side levers. These are the red levers I talked about earlier, and so you can change to more public transport, and you can turn your thermostats down if you want. Here's the thermostats lever, and it's all got little one-page guides that explain very transparently what each of the levers is doing, and here's your supply-side lever. So you can have a couple of Waleses of bioenergy if you want, and you can import another Wales of bioenergy from someone else's country, and you can see the effect that all these choices are having on your emissions and on other things that you might care about, including costs as well. So this is a tool for having grown-up conversations, and it's been used by government for government to have a grown-up description of what it intends to do. The Carbon Plan published in 2011 used this tool to describe the government's plans for how it will meet its legal obligations under the Climate Act. Here's the costs enumerated by the calculator. It shows how much your system costs, broken down into different categories, so that you can maybe do a bit of myth-busting about how expensive particular things are or are not. And all of the costs have error bars on them as well, which you can switch on if you want. These calculators have been made for other countries as well. China, India, Japan, South Korea all have 2050 calculators as well. And I think they're having an influence on policy making and hopefully on the public conversation in the countries that are democracies. So I'd love to play the game with you of making an Oxford pathway. No time tonight, but if you want to go play with the calculator is free online. And at this website, tinyurl.com/Oxford2050, I've got a blog post and a comments area, and you can all have a conversation with each other if you want. And I'll be back in March for the Oxford Literary Festival, and then we'll complete the crowdsourcing. We'll have the conversation in the room. We'll look at what everyone has said on this website as well, if any of you go there. And we'll come up with the Oxford pathway, okay? And see what Oxford wants to do to make a plan that adds up. Completely technology neutral. You can choose whatever mix of lifestyle, nukes, wind, biofuel, and anything you want, and we'll see what you actually want. And here's my prediction of what you will find when you choose that pathway. You will find, as we found in government, that any pathway that reaches the target involves the very large-scale deployment of technologies which today are still quite expensive or a bit risky and uncertain. And quite a few of those technologies have costs that come up front. Like you build a wind farm and you pay for it today, and then it has very low operating costs. Or you insulate a building really well per day, and that costs you a load to get the Polish builders to do the work for you. And then it saves you tons of energy for the rest of your life, but there is a big upfront cost. And that's a difficulty because people don't want to switch to a more expensive system. Bills is a very sensitive political topic at the moment with Miliband and Cameron saying things. And it's difficult if it actually costs in the first 5 years and then saves you energy thereafter, because 5 years is how long politics lasts. So that's difficult. So how can we fix that problem? Well, in red, my suggestion is innovation. Maybe the most important thing to be doing right now is, if you're an engineer or a scientist, go and innovate. And if you're not an engineer or a scientist, lobby Parliament to put more money into innovation support, because all of these low-carbon technologies, which you need for a plan that adds up, can credibly have their costs reduced, and there may be breakthroughs possible in them. So here's what I want for Christmas. I'd love it to be possible to retrofit a crappy old building in England up to Swedish building standards with amazing insulation that's far thinner than the rock wool, which was 12 or 20 centimeters thick. It would be nice for it to be cheap to install. We'd like electric vehicles that cost less than today's vehicles. They should have cheaper, lighter batteries. Maybe we need progress on supercapacitors. Lightweighting of vehicles in general would help a lot as well. And flywheels, maybe, to help store energy temporarily in cars. We need smart meters and smart controls that help people do the sort of thing I geekily did with my own eyeballs, reading meters and changing lifestyle. We need it to happen sort of without people even being conscious of it. We need heat pumps that work well. If we're going to have a pathway that switches us over to heat pumps, they better work roughly as well as I was saying, like the superhero, his Pumpu from Japan with cute eyes and gloves and a cape. We need the cost of wind to come down. Offshore wind seems to be politically acceptable, even with a narrative in government about saying how we've got to do everything with good value for money and growth is really important. Many people say, oh, but offshore wind is fine, even though it costs triple what today's electricity costs. It would be great to get the cost of offshore wind down, since it's not a politically unpopular technology with a lot of people. And so innovation support, it is happening. This is a product of Mitsubishi that's based on an Edinburgh inventor's design. Stephen Salter and his community invented digital hydraulics, and that's at the heart of this, which makes the wind turbine much more powerful and much cheaper than a standard turbine with a gearbox. Another radical thing to do with a wind turbine is to ask, well, where is the power really coming from in a wind turbine, and where is all the expense? And the answer is that most of the expense is in the mass of all the concrete and steel, especially in the tower, and maybe the gearbox. But most of the power is being generated by the tip of the blade as it goes around. That's where almost all of the power is coming from. The tip is the key thing. So here's an invention. Let's just keep the tip of the wind turbine and get rid of everything else. And you do that by putting the tip of the wind turbine on a piece of string to hold it in place, and you add a control system. So instead of using brute force, concrete and steel, to make the tip go round and round in circles, you say, let's have a control system, which means you have a little aeroplane with wing flaps and a control system that flies it round and round and round in circles, and you put a wind turbine on the aeroplane to take the power off that tip of this virtual wind turbine. This is 50 successive photos of the plane going around successfully in circles. Makani Power is the Bay Area company doing this. There's a couple of companies in Britain trying to develop kite power as well. So that's worth innovation support. Biomass. I came out with a sort of bad news story about biofuels at the beginning, but I do think that they have an important role. It's quite hard to make a pathway that adds up without some liquid fuels for some forms of transport and maybe some fuels for industry as well. And maybe those will need to be bioenergy, so we better have some breakthroughs in sustainable bioenergy. Nuclear power, it would be great to have nuclear power that's perceived to be more proliferation resistant, safer, and lower waste than today's technologies. And carbon capture and storage, I hopped over earlier. Again, breakthroughs could happen in this technology, and if we could get the costs of carbon capture and storage way down, that could really help with the global negotiations. To make the plan add up at all times, second by second, we need breakthroughs in storage, because at the moment storage is far too expensive for it to be credible to use lots of solar for most countries, unless the solar is well correlated with your demand already, like air conditioning. So we need breakthroughs in energy storage, and here's 3 companies that my innovation team at DEC was involved in promoting. One, making heat stores that can reversibly turn electricity into heat and back using an amazing heat pump. That's isentropic. Top middle, they're storing energy as hydrogen. You take electricity, you electrolyze water, and you make hydrogen more efficiently and with lower cost than standard electrolyzers. And on the right, SunAmp is an Edinburgh company that's taking electricity, using a heat pump to make heat and store it in a stratified heat store using clever chemicals so as to deliver heat to the house in a way that's much more responsive than the original heat pump. And you can run the heat pump whenever the electricity is cheap. So that's a lovely idea. Here's another breakthrough I'd like for Christmas. If we're serious about getting anywhere close to 2 degrees, we are going to need to suck CO2 out of the air with a giant vacuum cleaner. And so we need innovation support for developing vacuum cleaners. This is someone's visualization of them looking like cheese graters alongside a motorway. We need them so that we can suck millions and millions and millions of tons, actually billions of tons is the sort of scale we're talking about out of the air to bury in the ground. And that is in many people's pathways. It's an option in your 2050 calculator over here called geosequestration. It's a form of geoengineering. And interestingly, if you sneak a look at the Friends of the Earth's pathway, you'll find that they've got the geoengineering lever turned up to level 4, which means they're burying 110 million tons per year of CO2 in the ground. That's what a famous green group is advocating, having used our calculator. So geoengineering at a very large scale. And here's some other things I want for Christmas as backup plans. I think it's very important to keep working on hydrogen, even though in my book I said some critical things about hydrogen. I do still want to back the hydrogen horse, actually. And ammonia is a possible way of carrying hydrogen around that isn't quite as tricky to deal with as hydrogen. So maybe using ammonia as a fuel that doesn't involve carbon might be a good idea. And maybe we should be synthesizing fuels from thin air, grabbing CO2 and turning it into a fuel. And maybe if we're really trying to avoid global warming going above 2 degrees, we should be looking at other forms of geoengineering as well. So that's the sort of innovation I'd encourage. Also solar power and deep geothermal for other countries, though not especially for the UK. So what do we need to make a plan that adds up? What do we need for success? We can do it. This is what we need. We need the public and politicians to support a numerate approach. Let's actually talk about facts and realistic options. We need to base that on a realistic but ambitious energy model for each country that describes what definitely could be done and what could be done thanks to innovation support and really strong changes in policy. We need innovation support to drive down the costs of the low-carbon technologies, and we're going to need lots of well-trained engineers to go ahead and do the inventing and implementation and deployment of all this stuff that we need to build. I haven't quite completed all the pieces of bad news. Let me give you points 7 and 8, just so that I haven't misled you. Why is it still going to be difficult, even if we get the costs of those technologies down quite a bit? Well, if they're still a little bit more expensive than fossil fuels, then we still have an international and intergenerational commons problem. It's a tragedy of the commons. My 10 tons per year of pollution doesn't really hurt me very much at all. It just hurts everyone, all 9 billion people, equally a little bit. And so people don't feel the impact of their pollution. It's a tragedy of the commons, and commons problems are difficult to solve, but not impossible. You need to have some sort of binding agreement between people. And to get agreement to a binding agreement that actually works and does something, it needs to be perceived to be fair. And I think that's a big difficulty at the moment. It's difficult to get climate change action because people are negotiating in the wrong sort of way, so it's not clear what's fair. And this is now emphatically not government policy. I don't work for government anymore, so I'm allowed to say that I think these international agreements ought to be negotiating something different from what they're negotiating at the moment. Namely, I think they ought to be talking about what price carbon should have in future decades. Everyone agrees in economics there should be a carbon price, but lots of the economists say, oh yeah, so let's use cap and trade. That's wonderful, cap and trade, lovely. But I don't think that's a good way to negotiate, because if you're negotiating a cap for yourself and other countries are choosing their cap, you've got an incentive to cheat a bit and give yourself more of the cap than you really ought to. Whereas if you negotiate on price, and if you know that the price will apply to other countries, you've got an incentive to name a high price because you know it will apply by agreement to those other countries. So that's what I mean by a carbon price mechanism. It will give a predictable price. And you need to factor in compensation for poorer people to make them want to support it as well. So you have a proportional compensation to poor countries. Emphatically, not caps and not cap and trade. So I think problems 7 and 8 are solvable, but it's very difficult, and I think there needs to be a change in the approach to the negotiations to deliver that. If people want to read more about that, I recommend a paper by Crampton and Stoft called How to Fix the Inefficiency of Global Cap and Trade, which gives the game theory argument for why prices are a better thing to negotiate on than caps. Okay, so that was the sort of game theory geeky ending. That's my last slide. That's what we need to do. It's not easy, but it is possible, and if we get on with it, it may actually be fun. Thank you very much for listening.